Hi guys, welcome to my video on scoping in JavaScript. So about a week ago I kind of started a deep dive into how JavaScript really works behind the scenes, and part of that was learning about scoping. I made a blog post called Everything I Wish I Knew About JavaScript Scoping a week ago, which kind of goes into details about a lot of these things. But the first kind of chunk of that is really just about var versus let versus const, which are keywords for declaring variables, which to be honest I wasn't really that interested in the first place. And given that most people just don't use var anymore, I don't know how relevant it is. But I still think that scoping in general is pretty important to learn about. And I learned some interesting things about static scoping, dynamic scoping, and how it relates to the this binding. So my plan with this video is to take you through what I learned, and I'm going to try and take a experimental approach where I'm not going to make any claims without having some way of backing it up, which is why I've got this the Chrome DevTools open right now. We're going to try and understand how JavaScript works by actually observing what it does as a program runs. So we're starting with this program here, which basically declares a couple variables, A and B, and then declares this outer function. It itself declares two variables, C and D. Then it declares a inner function, which it itself declares two more variables, and then on the inside here we just console log all four. So a couple of these get overwritten. A does not get overwritten, but C does. So in here, it's called shadowing when you've got a function where another variable is in scope outside that function, but we're kind of overriding its value here. Well, I mean, we're not overriding the value of this variable, we just have another variable of the same name, and therefore we can't really access this variable. So we've got this function here, then we just call that function, and then we call the outer function. So the way the program works is we go here, declare this guy, call this guy, then we go inside here and declare this guy, and then we call it. So the point here is that we've got kind of nested scoping, and we want to see how these values end up coming out. So if I play this now, our console log shows A is 1, B is 5, C is 6, and D is 4. Okay, so A is 1 because it gets started here and doesn't get overwritten, or shadowed rather. B starts as 2, but then over here we've got B as 5, so we shadow this guy, and we just say, okay, we've got our own B variable here, which is equal to 5, so we use that. C is 3, but then over here it gets shadowed. We get a new C variable whose value is 6, so we end up saying C is 6. And finally D starts as 4 and does not get shadowed, so it's just 4 here. So off the bat we can see that when you have a function declared inside another function, it has access to variables defined outside of its scope, whether it's D in the outer function or A in this global context. Okay, so let's have a look at what's actually happening here. I've got a diagram that I made. Basically, JavaScript runs on an execution stack, which is equivalent to a call stack. At the bottom, we've got the global execution context. And so each of these little stack frames is called an execution context. So there's the global one at the bottom, which is this thing here, this scope here. Then we've got the outer execution context, which would be everything that happens in here would be happening inside that context. And then we've got the inner one, which would be this stuff. So what an execution context does is it basically just stores information you need to be able to know where you are at in a function, what the variables are that you might be reading from, and it's the kind of thing where if you turn the computer off and turn it back on again, and this stack was still here, and all the stuff that it pointed to, then you should be able to just continue the program from where you left off. So we've got our execution contexts on the execution stack, and each of these points to a probably more accurately has a reference to lexical environments. So lexical environments, when you see the word lexical, it basically means like letters or things you can see. In this case, we're talking about actual variables being defined. So a lexical environment just contains two things. It contains an environment record and a pointer to the parent lexical environment. So this happens to be called a declarative environment record, but what an environment record is effectively just a mapping of variables to their values. So in the case of our inner function, we've got b is 5 and c is 6. So that's these two guys. In our outer function, we've got c is 3 and d is 4, which are these two guys. And then in our global lexical environment, we actually have, this is it's a kind of weird edge case, but we've got a composite environment record consisting of two things: the declarative environment record, for which b is 2, and we have this other thing called the object environment record. So this is where things kind of get a bit weird. Back in the day, basically everything used these object environment records, and they would all have a thing called a binding object, which was a literal JavaScript object that just contained your variables as properties. It is still the case today that at the global level, if you define a variable with the var keyword, then it actually ends up just being a property on the global object. On the other hand, if you use let or const, it's going to be sitting in this declarative environment record. Now, what's the difference? First of all, when you actually have an object environment record, the binding object, in this case global, just can be accessed by outside code. And it's not very efficient. So these declarative ones, they're kind of internally stored, and it's not accessible from the outside. Okay, so the fact that these all point to each other allow us to create a scope chain where we can say, I'm in the inner function, I'm looking for the a variable right now because I want to log it, and it's not in my declarative environment record. So therefore I'll look to my parent. It's not in there either. I'll look at my parent. Oh, here it is on the global object. So you can get the value of 1, and then you can log that value. So it's probably also worth noting that these functions, when they're created, they actually get a internal reference to the scopes that they have access to. So let me go down here, and actually got to refresh the page. If I go debugger and then play that, okay, so if I look at the inner function, you can see here, this is just in my DevTools inspector. Within scope, I've got my inner function, it's got arguments, it's got a prototype, but it has this internal thing, and these internal things are denoted by these double square brackets. This guy's called scopes. And in this case, we've got a few things. So we've got the value of d from our outer function, the value of b from a script. Anything that's defined at the top level with let or const is considered to be script scoped, which is not the same as saying there's actually only scopes to the... We're talking about actual script tags here. If I go, for example, this thing would be a script tag. It's not actually scoped to the script tag, it's just any script will have access to it. And then we've got the global thing here. So if we expand this guy, we'll see that actually among the many properties of the global object, one is a whose value is 1. So that's this guy here. So kind of weird, but also pretty cool. So let's move on, and I'm going to go to the next example. So in this case, we've got an inner and an outer function, but our inner function is actually defined outside the outer function. So when this guy's defined, it references x, but the x is actually defined in the global execution context, and the outer function, basically when it gets called, it goes and creates its own local x variable, and then it calls inner. So the question here is, which x will this inner function log? It turns out that when you run this guy, it's going to log 1, which means it logs this thing. So this kind of touches on the difference between static and dynamic scoping. In static scoping, when a function is created, any variables that it references from an outer scope, it looks at, okay, like lexically or statically, that's why it's called static scoping or lexical scoping. What have I got access to? So I can just look on the page here and see, okay, well, there's an X that's in scope here, so that's what that's referring to. What actually, is defined against a function that might be calling my inner function, it doesn't matter. So that's called static scoping, which is to say that you can just statically look at the page and know which variables here are being referenced. Now, you might ask yourself, isn't this what every programming language does? And actually, no, it's not. So here we have a bash script. I'm just going to paste this in here. So in this script, we do the exact same thing. We define X, we've got an inner function that just logs it, an outer function that defines its own X and calls the inner function, and then we call the outer function. So we're going to go X is 1, call the outer function, go in here, create X equals 2, call our inner function, and then echo X. We press this, if we play this. Okay, so this actually logs 2. So what this means is that Bash does not use static scoping, it uses dynamic scoping. Dynamic scoping is where you care about what variables are defined at call time. Meaning, at the time this guy is called, we look at, okay, what's the value of X? So like we're in here, we go, okay, we need the value of X. Instead of looking lexically, statically up to whatever was defined at the point when this guy was created, in which case X would be 1, we instead say, well, who called us? Okay, well, we're being called by outer. Is there an X defined in this scope? Yes, there is. Okay, let's log that. So a diagram that explains this discrepancy would be this. So let's assume that Bash itself had a concept of lexical environments, which it doesn't, but if it did, then this is the difference between how the two would operate. So in this case, we've got our inner function, doesn't have an X defined. So in JavaScript, we go, well, somehow we know that the parent lexical environment is actually the global environment, because when this guy was defined, I'm just going to go back. When this guy was defined, it was lexically in scope here. This, we didn't care about the outer function at the point this was created. So we go here and we find X is 1 and we log that. On the other hand, Bash just follows the actual stack frame. So it goes, okay, nothing's defined here. Okay, what about the guy that called me? Oh, it is defined there. Okay, well, I'll return that. So different languages have different approaches to this. So for example, in Perl, you can have both dynamic or static scoping, depending on how you declare your variables. They've got different benefits for different use cases, but generally it's considered that static scoping is superior because it enables, there's a few reasons, one of which is you can more easily reason about how a function will behave. So for example, in this case, I don't need to care about, once I've defined this function, I know that this guy's in scope and so it's referencing that. I don't need to worry about whether in some other file, some other function is calling me and it defines X in its own weird way. So to understand how a single function will work, all I need to do is look at the page or look at the file it's defined and look at the scope it's defined in and I'll understand. With dynamic scoping, you need to think about all the permutations and understand, who knows what variables could be set when I'm being called by some random outer function. Dynamic scoping does have one benefit, which is that you don't need to worry about storing variables on the heap. So, assuming we're talking about primitives like booleans and integers, you can just keep everything on the stack here, and as soon as you're done with the function, you just, drop down the stack pointer, free out the memory. When you enter a new function, you put a new stack frame on the stack, move the pointer up again, and basically, whenever you need to look for a variable, you just look down the stack until you find it. In JavaScript, we need to kind of have some additional metadata that we hold on to. For example, to say that this inner function was really defined with this guy in scope. At the time we didn't care about the outer function, so we need to skip this guy because we're doing static scoping. The fact we have to store those kinds of references means we can't do it all on the stack. It's not as simple as just looking from top to bottom. But let's continue. So there is another way in which static scoping helps us, and that is in how closures work. So a closure, it kind of has two definitions. The first definition of closure is a function that is paired with it's paired with this environment. So it's a function that kind of has knowledge about where it was, for example, created and what variables were in scope at that point. There's another definition of closure, which is just referring to the environment part. Like, the closure is just the things that are captured, the variables that are captured. So the two are kind of used interchangeably, but they're effectively referring to the same concept. In this case, we have a function, we define x, and we have an outer function now. That defines an inner function internally. Outer has its own x, whose value is 2. And what happens here is the outer actually returns inner, so it returns a function. So in JavaScript, functions are first class, which means that you can pass them in as arguments to functions, and you can also return them from functions. So you can treat them like any other variable. So what's happening here is we're actually capturing this x value here, and we're capturing this one because lexical scoping says that we first look at, what's in our immediate scope here. Oh, the value is x. Okay, well, we'll just capture that guy. We return the inner function, and then we assign that to this variable foo. So we're calling outer, it returns inner, so now foo's value is inner. Then we call foo, which is the same as calling our inner function. And the question is, what does it log? So if you run this, we log the value of 2. So, okay, what's interesting about this is that this variable 2, which is defined in that outer function, really has no reason to exist after we leave the call to outer, if not for our inner function, which kind of captures that variable. So I say capture, another word would be close over. The reason it's called capture is because we need to hold on to this thing after the lifetime of our outer function. So if we, for example, were just storing everything on the stack here, we'd have our outer function, we'd have our inner function, we'd have x equals 2 happening here, and we'd eventually have to pop off the stack and get back to our global execution context when we're down here. But once we want to then call our inner function again, we need to have some way of keeping track of the fact that it has this variable x equals 2, which isn't actually defined in its scope. So let me grab this diagram. So what's happening here is that by the time we get to foo, which is really just a variable pointing at our inner function, it has nothing defined in its lexical environment. And because we use static scoping, it just so happens that this function contained a reference to the lexical environment of the outer function, where x equals 2, and so we can say, okay, x equals 2. Obviously that also points to the global environment record. Now, if we were using dynamic scoping, what would happen here? Effectively, we'd have a foo function here. We'd be calling it in the global context, meaning this guy is in scope, and this guy is not. And we'd be going console log x, and we just look down the call stack. So foo, we don't have it. Global context, we do have it. The value is 1, so we'll return 1. So effectively, dynamic scoping does not support closures, unlike static scoping, which will allow you to kind of store these guys in memory somehow, and then later on you can access those variables and change them or just read from them. So I'm just going to start this again, just so we can see what's actually happening here. So our foo function has some scopes, and we've got a closure here, so it closes over x. Then the next one up, we've got our script, for which x equals 1, and then the global object. So these two guys are kind of two parts of the composite environment record that happen in the global execution context. So it's kind of interesting, and if I go in here, it's effectively the same thing. We have this, in this scope here actually now, forget about the function. So just in this scope, when we're trying to console log this thing, we've got access to this closure, which was saying x equals 2. That's pretty cool. Now, let's look a little bit deeper into how, for example, Chrome, which uses the V8 engine for JavaScript, actually goes about creating these closures. Now, this is where we kind of diverge in terms of what ECMAScript says we should be doing or what it's specifying, and how the ECMAScript is actually implemented. So ECMAScript is the specification for the JavaScript language, and different browsers and, for example, Node would have their own implementation. So, for example, the V8 engine that Chrome uses is written in C++, and it kind of compiles JavaScript on the fly while it runs it and tries to optimize things as it goes. But as you can imagine, the ECMAScript approach is a little bit flawed. So, if you have a bunch of variables defined in a function and only one of them gets captured by an inner function, and then you return from the outer function, you don't really want to be holding on to all of the variables in that lexical environment past their expiry date, basically, because no one's going to use them if you've only captured one variable. So what V8 does is kind of intelligent, but I'm going to show you what it does. So in this program, we've got an outer function. We define 3 different variables, x, y, and huge. So huge, let's just pretend this is a really big object. And we have we've got one function here called bar, which captures the huge variable, so it references that. Doesn't reference these two guys though. Then we have an inner function which captures x, but doesn't capture these two guys. And then we return the inner function. So bar is defined, but doesn't actually get used. On the outside, we do the same thing as before. We call our outer function that gives us this, so we assign it to foo, and then we call foo. Okay, so let's have a look at how this actually works. So if I play this now, we've created a foo object. So I can have a look in here, and it's got scopes. Now, interestingly, this guy is now, it has a reference to a closure from the outer function, because the outer function is now returned, and it actually refers to 2 different things. So it actually has a reference to x, which it explicitly captured, but also our huge object. Now, it's good to know that it doesn't have access to the y variable, because that would be a waste of memory, because no one actually makes use of that. But, what does the inner function care about the huge variable? It doesn't make use of it, it only cares about the x variable. So if we continue again, and we look at the actual closure that we have in our outer function, look at that. So we've got both of our things here that were captured. So what this tells us is that in the V8 implementation of closures, effectively the way that it works is as soon as we, I'll probably actually put it, let me refresh this, debugger, save, oops, do it again, debugger, I did it again, okay, this time will definitely work. It's annoying that you have to do this. Save, play, alright. So in here, let's have a look. So we have debugger, we're being called script global bar inner this, okay, bar inner. So this is just these guys being hoisted, as is y. Funnily enough, x and y, sorry, x and huge don't appear in my local scope. I can't see them in the, they're not really in a closure. If I continue again, then they appear here. Interesting. So what we'll do is, later on I'm going to show kind of what really happens on the actual heap, because the Chrome DevTools let you actually inspect heap snapshots. But for now, I'm just going to continue, and we're going to talk about this variable. Okay, so I have said so far that the JavaScript uses static scoping, which is for the most part true, but there is one notable exception, and that is the this binding. It's not really a variable because its value does not vary once you're inside the scope. It just kind of gets given a variable, and that's what it is. So the way that it works is it's effectively, well, I'll show you an example. So here we set x to 1, then we create an object. It's got a couple of properties, x and a. A is a function that just logs x, and this is really just a demonstration of how things get weird pretty quick. So we have a bar variable, and we're just setting that to the value of object.a, so this is now going to be this function here, and then we also can just call object.a directly. Funnily enough though, this gives 2 different values. So if I play this, go to my console, 1 and 2, okay, bizarre. We've got the exact same function, but depending on how we call it, we get a different value. So in the case of bar, we get x, and in the case of object.a, we get 2. So what's going on here? So the way that it works is, if you have a function and it contains a this binding, the value that's passed in is actually based on the way in which you call that function. So if you just call it directly, then it's going to be given the value of the global object, which is basically a object that contains this x as a property. Whereas if you call it, so if on the left-hand side of these brackets, these parentheses, you have what is called a reference type, then it's actually going to be given this variable, or this binding, will be given the value of the object itself. Meaning when we try and call the x property on that, it's going to be this guy. So what's going on here? So a reference type is basically, you can actually check this in brackets and it will still work. Hang on, let me copy this, refresh, do that, save, play, same thing, same thing. Yeah, so what this actually is before it evaluates to the actual function, it evaluates to a reference type. And a reference type is just when you have an object and then you're calling some property on that object. So in this case, it's object.a. So whenever you do that, and then you have the parentheses here, what it means is it'll invoke this function, but it will set this binding to the value of the actual object. Strange. Why would we violate static scoping in this way, right? When this thing is defined, it's with the way you call it, as opposed to the way that you create it, which is more of a dynamic scoping thing, will influence its value. And basically what this enables is sharing of code. So we can have two objects here, and a foo function that makes use of the this.x reference. You can then assign that to both of these objects, and then you can call them, and you'll get different values because the different objects contain different values for x. So effectively, because functions are first class, it would be a shame if we couldn't actually kind of make use of this neat functionality to have kind of genericized logic that can be applied to different objects and different data. There is another example of how this works, which is when creating prototypes. So I won't go into too much detail about prototypes here, but prototypes are effectively the way that JavaScript enables inheritance. So we've got a kind of constructor function here, and it says, okay, you give me an object, like an empty object, and I'll set x to 1 on that object, and I'll set the blah property to this function that just console logs something. And then I can say on here, I can set the prototype of this function, which is a fancy way of saying, when I create an object from this guy using the new keyword, I want this object's prototype to have this additional functionality. So in this case, I'm saying I've got a foo property, and it has a function that console logs this.x. And if I go and create my a object, I'll get an object that just says x is 1. And then if I call foo on that, because I'm making use of the this keyword here, I'll be referencing this x, because I'm using a reference type here. So if I play this, 1. Okay, cool. So what this enables is basically inheritance. I can have multiple different objects here. I can go b, and I can say a.prototype equals b.prototype, and make that 2, make that haha, and I can go, let's see here, I can do object new b, and then this will be 2, and then it should log 2, so let me just save this. Whoops. Oh no, I've lost it. Oh, it's alright, I can just do it again. So, okay, I've got a b constructor, value is 2, this says haha. I'm going to say b.prototype equals a.prototype, and then make this a b, this guy's going to be 2, and save and play. Now it logs 2. Okay, cool. So what this says is basically we've got two completely different constructors here, but they both inherit from this same kind of prototype, which has this function on it where we can just say just console log this.x, and there you go. You can create, effectively we've created a taxonomy. A and B both inherit from some prototype that defines some behavior that we can call if the property itself doesn't exist on our base objects. So through this binding, we basically enable these prototype chains to define shared behavior among the descendant objects. Pretty cool. So this is what, I mean, so static scoping on the whole pretty good, but sometimes it is worth it to go for the dynamic approach if it enables things like, in this case, sharing code and inheritance. Okay, so in this case, this is just an example of where it can get a bit weird, and you might want to switch up what you're doing. So here we have a constructor function called foo, we set x to 1, and then we say set timeout, and then when the timeout, when a second passes, we're going to console log this.x. Okay, and then we go f equals new foo. So if we run this, what's going to happen? 1, 1. Let's have a look at that. Console log this.x. Why is it going 1, 1? Let's try this again. Oh, because I hadn't cleared my console. Okay, good. So it's logging undefined. Kind of weird. It's saying this.x and this.x is 1, so why would that be happening? The reason is because when we go set timeout, this guy gets added to our event queue, and when it finally gets popped off and gets ran, it's ran on the global execution context, meaning it's not being called as, you know, f dot blah. It's just being called directly. That means it gets past the global object as it's this, and the global object does not define ax. If it did, it would log that. So if I go x equals 2, I think this will work. Maybe it won't, but let's find out. I'm going to refresh. I'm going to paste. Then I'm going to save. Then I'm going to play. 2. Okay, cool. So yeah, it gets past the global object. So this is kind of weird because we really want to just be able to reference the this that's defined, you know, inside this scope. So what can we do? Let's go to the next example, and what you can do is, this is the exact same thing. We've just swapped out our function declaration for a lambda expression. These are added in ES6, and basically now if you play this, it, don't know what, yeah, 1, there you go. So I had to wait a second. Okay, so what's the difference here? So the use of the lambda expression is really a way of forcing static scoping when otherwise this binding would be making use of dynamic scoping. To demonstrate, let's have a look at what it actually does behind the scenes. So if we go to this Babel REPL, it shows on the left-hand side, this is the exact same thing we have here, and we're saying set timeout, we're using a lambda function, and this is what it actually transpiles to. So what we get is, inside here we say, first of all, let's just keep track of what our this variable is inside this scope, and then it means that when we create this function here, and so see how it's lambda here, but it's not lambda here, so this is really just under the hood, a regular function. What we're doing here is that we're now, instead of using this directly, because we know this thing is kind of unreliable and its value changes, let's refer to this statically defined this variable, and we'll call x on that. And so then when we log that, that's why we get this value of 1. So effectively what using a lambda function does is it basically forces JavaScript to make use of static scoping by, under the hood, going and actually adding a variable to this lexical scope, and it means that you're not worrying about what the value of this is when this guy's actually invoked. So yeah, it's cool. So the this binding gives you some cool benefits when you want them. When you don't want them, there's typically ways to get around having to use it. Another way would be calling .bind on a function and passing it the value of the current this. But I'm not going to go into that just now, because I say the end, but there's actually one more thing I want to show you guys. Okay, so here we're going to look at actually what happens in terms of the heap when we are dealing with closures. So it's a similar function to what we had before. We've got an outer, we've got a inner, we've got a bar that doesn't really get used, and we just call everything at the end. So let's run this guy, see what happens. Okay, so we've defined our outer function, and actually let me just play through here. What actually happens here? Something's undefined. Okay, what I'm going to do is I'm going to, every step of the way here, I'm going to actually take a snapshot. This is a heap snapshot, and it basically goes and tells you what are all the things that have been actually, like all the objects that have been put on the heap at this point in time. So I'm going to play forwards, I'm going to take another snapshot. I'm going to go again, take another snapshot. I'm going to go again, take another snapshot. And then I'm going to go again, and I think one more snapshot. Okay, cool. Now what I'm going to do is, I'm going to, in each of these places, only show the difference between the current snapshot and the previous one. So, make sure that all makes sense. Okay, cool. So this is showing us the difference in what's been allocated, what's been newly allocated between, let's turn my alarm off, between one snapshot and the next one. So, okay, snapshot 2, let's have a look at what happens inside here. So we've got, back to our sources. So that's looking at this guy. So we create our outer function. Okay, so we've got a closure being created here. Oh, interesting. So by the time we get to the end of, by the time we get to here, we've created this function, and it has a closure object here. So this is 124913. It's got a context. The preview, okay, that's got a lot of random stuff there. Okay, so interesting. All right, let's look at what snapshot 3 gives us. Okay, so this is creating a closure. This guy's creating a context. So in V8, there's a thing called a context, capital C, not to be confused with an execution context. And let me get rid of it. Okay, so let's see what we're actually creating here. Okay, so snapshot 3. That's 1, 2, 3. So at the very beginning, when the code enters our outer function, we have already made a context object, which is going to store the two things which are being captured here. So bar string and inner string. Okay, let's have a look at this. So bar string is captured by bar down here. Inner string is captured by inner down here. And uncaptured string is actually not captured by anyone. We just define it and then we don't use it. So this is interesting. So as soon as we're here, JavaScript clearly goes ahead and before it actually goes and continues running the code, it goes and says, okay, here's all the things that get defined in our scope. Okay, who's going to be using those things? Who's going to be capturing those things? Whoever, if anyone inside here, if any function captures these variables, then we need to actually create a context object and put those variables on that context. So here we've got 125119. Okay, interesting. We move on, and here we enter a block. Now this could have just been like if, true, but you actually don't need to have that. You can actually just enter a block directly, which is it's a feature no one uses, but I feel like maybe we should use it a bit more to kind of limit variable scope. But at any rate, it's just here for demonstration purposes. So here we enter the block scope, and here we have a block string, which is captured by bar. So if I look in my memory on snapshot 4, we get another context here, okay? And it's not really telling us much right now, but it has as its previous context, so it's like a reference to the parent context, the same guy we saw before, 125119, so that's the same as this guy here. And it's got, both of these strings now have values by the time we get to this point in the code. So yeah, funny that we don't have our, this guy defined, but maybe it's slightly different behavior between functions and blocks. But at any rate, let's go to the next snapshot. So let's see, the next snapshot is, the final one is this guy on the other side of bar. Okay, so now we have a closure. So that means that we've got our bar function, and it now references this context. So 125313, that's the same as this guy. And what's inside here? Okay, so now it has, funnily enough, it has, it knows what the value of this thing is, this block string, but it doesn't say what the name is. I don't know why that is. Maybe it doesn't need it. Maybe it's going to be minified. But at any rate, it's been captured. And then here we've got a pointer to our previous context, which has our other two things that are captured as well. So what that tells us is that these context objects exist in a given scope, and they whatever variables from that scope get used by other functions in that scope, or like descendant scopes, those will be the ones that end up being added to the context. And then when you actually return one of these functions, for example, let me go here and run that. So right now in my scope is That's kind of weird. Why is F not in here? Oh, because I haven't... Right, yes, very good. Let's call it a const. Fresh. Paste, save, play. Quite on the same thing? Outer. I think it's behaving differently because of the fact that I need to just change the actual source code. Let's do that. Start again. Ooh, disconnected. And here we go. Okay, that's better. Cool, so now we have, we can see here we've got this closure that contains the things we cared about for our inner function. It does not contain the closure that was made for this guy because that's in its own block, but clearly this guy does have access to this closure that was defined right up here. It contains not only inner string, which this guy explicitly captured, but also bar string, which this other guy captured. So something to keep in mind. If you have a huge, if you've got two functions closing over a bunch of variables, and one of them closes over some huge object, and the other one doesn't, but the other one lives on past the lifetime of the parent function, then you might be holding onto that object in your heap in memory for longer than you want to. But that effectively wraps this up. So hopefully this was a good intro to JavaScript scoping and how it balances static scoping with dynamic scoping, how it supports closures, and what actually happens on the heap when we are dealing with creating closures. So yeah, thanks for watching, and I'll add a link in the description to the original post, which goes into some more detail about what's going on behind the scenes. All right, thanks for watching.